Welcome to Sleepy Science, a calm place where we explore the quiet mysteries of the universe together. If you enjoy relaxing science stories like this, remember to like the video and subscribe to the channel, and write in the comments where in the world you are watching from. It is always wonderful to see how far these stories travel across our planet. Now settle in, relax your mind, breathe slowly, and allow your thoughts to drift gently into one of the most fascinating regions of the cosmos, the mysterious world of black holes. The universe is unimaginably vast, filled with billions of galaxies, and inside each galaxy, there are billions of stars surrounded by planets, clouds of gas, drifting dust, and silent cosmic structures that slowly shape the universe over immense periods of time. Yet among all of these celestial objects, there are places where gravity becomes so strong that even light cannot escape. Regions where the normal rules of space begin to bend and twist, and these extraordinary places are known as black holes. Despite the name, a black hole is not an empty hole floating in space. It is actually one of the most dense and powerful objects that can exist in the universe. A black hole forms when an enormous amount of matter becomes compressed into an incredibly small region. When this happens, gravity grows stronger and stronger until it overwhelms everything around it. The pull becomes so intense that anything that comes too close will be captured forever. Light itself cannot escape this pull, and because light cannot leave, the black hole appears completely dark to us. To understand why black holes are so powerful, we can think about gravity in everyday life. Here on Earth, gravity quietly holds us to the ground. It keeps the oceans from drifting away into space and keeps the atmosphere wrapped gently around our planet. The Earth has a certain amount of mass, and that mass creates the gravitational pull we feel every moment of our lives. The Sun is much larger than Earth and has far more mass, which is why its gravity is strong enough to hold all the planets of the solar system in their long, slow journeys around it. But imagine something far more extreme. Imagine taking a star much larger than the Sun and compressing all of its mass into a region only a few kilometers wide. The same amount of matter would still exist, but it would be packed together with incredible density. In such a situation, gravity would become unbelievably strong. Space itself would begin to curve dramatically around that point. Time would slow down. Light would struggle to escape, and eventually, a boundary would form around this region from which nothing could return. This invisible boundary is what makes a black hole so unique. Outside this boundary, objects may still escape if they move fast enough, but once something crosses that invisible edge, the journey becomes one way forever. The gravity beyond that point is so overwhelming that every possible path through space leads deeper inward. Not outward, not sideways, but inward toward the hidden center. Black holes were once only theoretical ideas imagined by physicists trying to understand gravity. For many years, scientists wondered whether such strange objects could really exist in nature. But as telescopes improved and our ability to observe the universe grew stronger, astronomers began to notice unusual signs in distant parts of space. Stars orbiting something invisible, bright disks of glowing gas swirling rapidly around dark centers, powerful jets of energy shooting across entire galaxies. Slowly, the evidence became impossible to ignore. Black holes were not just mathematical curiosities. They were real objects, scattered across the universe, shaping galaxies, influencing stars, and quietly sitting in the centers of cosmic systems that stretch across millions of light years. Today, scientists believe that most large galaxies contain a supermassive black hole at their center. Even our own galaxy, the Milky Way, holds one deep in its core, hidden behind clouds of dust and distance, yet controlling the motion of countless stars that slowly orbit around it. Yet even though we now know black holes exist, their true nature remains one of the deepest mysteries in science. What happens to matter that falls inside them? What happens to time? What happens to space itself? And what truly waits at the center of a black hole remains one of the most fascinating questions in the entire universe. And as we continue this quiet journey through the cosmos, the deeper we look into black holes, the more the universe begins to reveal how strange, beautiful, and mysterious it truly is. When we look up at the night sky, the stars appear calm and unchanging, tiny points of light quietly shining across the darkness. Yet, every star in the universe is living through a long and dramatic life cycle that can last millions or even billions of years. Stars are not eternal objects. They are born from clouds of gas. They grow brighter as they age, and eventually they reach a moment when their life begins to change forever. Some stars end their lives gently, slowly fading away into smaller objects. But the largest stars in the universe experience a far more dramatic ending, an ending that can create one of the most powerful objects known to exist, a black hole. A star begins its life inside enormous clouds of gas and dust drifting through galaxies. These clouds are mostly made of hydrogen, the simplest and most common element in the universe. Over long periods of time, gravity slowly pulls parts of these clouds together, gathering gas into denser and denser regions. As the gas compresses, it begins to heat up, and eventually the center becomes hot enough for nuclear fusion to begin. At that moment, a star is born. Inside the core of a star, an incredible process takes place. Hydrogen atoms collide and fuse together, forming helium and releasing enormous amounts of energy. This energy pushes outward from the center of the star while gravity pulls inward. As long as these two forces remain balanced, the star stays stable, shining steadily across space for millions or billions of years. For stars similar to our sun, this balance can last an extremely long time. The sun itself is expected to continue shining for roughly 10 billion years in total. But not all stars are like the sun. Some stars are far larger, containing many times more mass. These giant stars burn their fuel much faster, living shorter but far more intense lives. As a massive star ages, it begins to run out of hydrogen in its core. When this happens, the delicate balance between gravity and energy begins to shift. The core starts to contract under its own weight, while the outer layers expand outward. The star grows larger and larger, becoming what astronomers call a red giant, or in even more extreme cases, a red supergiant. Inside the shrinking core, temperatures rise to incredible levels, allowing new types of fusion to begin. Helium fuses into heavier elements, and eventually the core may begin producing carbon, oxygen, silicon, and other elements. Each stage burns faster than the one before it, and the life of the star begins to accelerate toward its final moments. Eventually, the star reaches a critical point when iron begins to form in the core. Iron is a special element in stellar physics because fusing iron does not release energy. Instead, it consumes energy. This means the star can no longer produce the outward pressure needed to balance gravity. Without that support, the core collapses in an instant. The collapse happens with extraordinary speed. In less than a second, the core of the star shrinks dramatically, and the outer layers crash inward. The pressure and temperature rise to unimaginable levels. This sudden collapse triggers one of the most violent explosions in the universe, a supernova. For a brief moment, the exploding star can shine brighter than an entire galaxy. Matter is blasted outward at incredible speeds, spreading heavy elements across space. These elements eventually become part of new stars, new planets, and even the atoms inside living beings. But deep inside the remains of that explosion, something remarkable may form. If the original star was massive enough, the collapsing core continues compressing under gravity. Matter becomes so dense that the atoms themselves begin to break apart. Protons and electrons crush together, forming neutrons. If the mass is large but not too extreme, the core stabilizes as a neutron star, an object so dense that a teaspoon of its material would weigh billions of tons. Yet if the core is even more massive, gravity refuses to stop. The collapse continues past every known limit. The matter compresses further and further until the density becomes almost impossible to imagine. At this stage, gravity overwhelms every force that normally holds matter apart. The core collapses inward until a black hole is born. At that moment, a region forms where gravity becomes so powerful that nothing inside a certain boundary can escape. Space bends inward toward the center. Light itself becomes trapped. The remnants of a once enormous star become something completely different. A silent region of extreme gravity hidden within the vast darkness of space. Black holes may appear quiet from a distance, but their creation begins with the explosive death of a giant star. And from that moment forward, they begin a long and mysterious existence, slowly interacting with the universe around them while hiding their deepest secrets behind an invisible boundary. When people imagine a black hole, they often picture a dark hole floating in space like a cosmic vacuum cleaner pulling everything into a bottomless pit. In reality, the structure of a black hole is far more subtle and far more fascinating. A black hole is not a hole in the traditional sense. It is a region of space where gravity has become so intense that the geometry of space itself begins to curve inward dramatically. To understand what truly exists around a black hole, we need to imagine a layered structure made of invisible boundaries, regions where the behavior of matter, light, and time slowly begins to change. Far away from a black hole, space behaves mostly normally. Stars can orbit peacefully and light travels in straight lines across enormous cosmic distances. But as an object moves closer to a black hole, the gravitational pull becomes stronger, and the environment begins to change in ways that feel strange compared to our everyday experience. The first region surrounding many black holes is not completely dark at all. In fact, it can be one of the brightest places in the universe. When gas dust, or even entire stars, drift too close to a black hole, they begin to fall inward under the force of gravity. Instead of dropping directly into the center, the material usually begins to spin around the black hole, forming a rapidly rotating disk. This glowing ring of extremely hot matter is called an accretion disk. Inside an accretion disk, the material moves at incredible speeds, sometimes reaching a large fraction of the speed of light. As the gas spirals inward, it becomes compressed and heated to extraordinary temperatures. Friction between particles releases enormous amounts of energy, and the disk begins to glow with intense radiation. To distant telescopes, this glowing disk can outshine entire clusters of stars, making the region around the black hole appear brilliant rather than dark. Closer to the black hole, gravity becomes even more extreme. Light traveling through this region begins to bend noticeably, following the curvature of space itself. Instead of moving in perfectly straight paths, light rays arc and twist around the black hole, creating strange visual effects. If you could observe this region directly, you might see distorted images of distant stars stretched into curved rings around the darkness. Eventually, we reach one of the most important boundaries in the entire universe. This boundary is known as the event horizon. The event horizon is not a solid surface, and it is not something you could touch with your hand. Instead, it is an invisible border in space, marking the point where escape becomes impossible. Outside the event horizon, an object could still theoretically escape if it moved fast enough. A spacecraft with powerful engines might still climb away from the black hole if it remained outside this boundary. But once something crosses the event horizon, every possible path through space leads inward toward the center. The escape speed beyond this point becomes greater than the speed of light itself. Because nothing can travel faster than light, nothing can escape once it passes the event horizon. Not a spaceship, not a beam of light, not even a signal carrying information. From the outside, the event horizon appears to be the ultimate edge of the black hole. A silent spherical boundary beyond which the universe can no longer observe what happens. To a distant observer, something falling toward the event horizon would appear to slow down more as it approaches the boundary. The light coming from the falling object becomes stretched and dimmer until it slowly fades from view. From far away, it almost looks as if the object never quite crosses the horizon at all. Instead, it seems to freeze near the edge, and gradually disappear into darkness. But for the object itself, the experience would be very different. From its own perspective, time continues normally, and it would pass through the event horizon without noticing any visible barrier. There is no wall and no sudden shock. The crossing itself might feel strangely ordinary, even though it marks the beginning of a journey from which nothing can return. Inside the event horizon, the structure of space changes in ways that are difficult to imagine. All directions begin to lead toward the center. Moving forward in time becomes similar to falling deeper toward the core. The deeper one travels, the stronger gravity becomes, until eventually everything is pulled toward the mysterious heart of the black hole. At the very center lies the most mysterious region of all, a place known as the singularity. In this region, the density of matter may become infinite, and the curvature of space may grow beyond anything our current understanding of physics can fully describe. It is a place where many of the laws that govern the universe begin to break down. Black holes, therefore, are not simple objects, but layered structures of gravity and warped space. From the glowing accretion disks surrounding them to the silent boundary of the event horizon, and finally to the hidden singularity deep inside. They represent one of the most extraordinary environments in the entire cosmos. And even though we have learned a great deal about their structure, the deeper we explore the nature of black holes, the more mysterious they become. Quietly waiting in the darkness, while holding some of the universe's most profound secrets. As we continue drifting deeper into the quiet mystery of black holes, we arrive at one of the most fascinating boundaries in the entire universe. A boundary that is not made of matter and cannot be touched, yet it defines the moment where escape from gravity becomes forever impossible. This boundary is called the event horizon, and it is one of the most important ideas in understanding what truly happens around a black hole. The event horizon is often described as the edge of a black hole, but in reality, it is more like a border in the fabric of space itself. Nothing special marks this boundary visually. There is no glowing line and no physical wall. Yet mathematically and physically, it represents a profound transition between two different regions of reality. Outside the event horizon, space still behaves in ways that we can understand. Gravity may be extremely strong, but objects can still move freely, and signals can still escape if they travel fast enough. Spacecraft could, in theory, orbit the black hole at a safe distance, just as planets orbit stars. Light can travel outward and reach distant observers. The universe outside remains connected, but as an object moves closer to the event horizon, gravity becomes more and more intense. The paths that objects follow through space begin to curve inward. Escaping requires greater and greater speed. Eventually, the required escape velocity reaches the speed of light itself. At that exact distance, the event horizon forms. Inside this boundary, every possible path through space leads deeper toward the center. Even light, which normally travels faster than anything else in the universe, cannot climb back outward. The geometry of space has been bent so strongly that outward paths simply no longer exist. To understand this idea, it helps to imagine standing beside a powerful waterfall. Far upstream, the river flows calmly, and boats can move in any direction. But as the water approaches the edge, the current becomes stronger and stronger. At some point, the flow becomes so powerful that no boat engine could move against it. Once a boat passes that invisible line, it will inevitably be carried over the waterfall. The event horizon behaves in a similar way. Space itself flows inward toward the center of the black hole. Outside the horizon, objects can still move against this flow if they have enough energy. But once the horizon is crossed, the inward motion of space becomes unstoppable. One of the most fascinating aspects of the event horizon is how it appears to distant observers. If someone were watching a spacecraft slowly fall toward a black hole, they would see something very strange happen as the craft approached the horizon. Because gravity affects time, the clocks near the black hole begin to run more slowly compared to clocks far away. This effect becomes stronger the closer an object moves toward the event horizon. From the viewpoint of a distant observer, the falling spacecraft appears to slow down more and more. The light coming from the spacecraft also begins to stretch. As the craft moves deeper into the gravitational field, the wavelengths of the light grow longer and redder. The signals become weaker and dimmer. Eventually, the spacecraft appears almost frozen near the horizon, fading slowly as the light loses energy. To the distant observer, it might seem as if the spacecraft never quite crosses the boundary at all. Instead, it appears to hover forever near the edge before gradually disappearing from view. But from the perspective of the astronauts on board, the experience would feel completely different. Their clocks would continue ticking normally, and they would not see the universe freeze outside. As they approached the event horizon, nothing dramatic would suddenly appear. There would be no visible surface and no sudden flash. In fact, the crossing itself might feel surprisingly uneventful. The spacecraft would simply pass through the invisible boundary and continue falling inward. The outside universe would still be visible behind them, although it might appear increasingly distorted by the extreme curvature of space around the black hole. Yet, even though the crossing might feel ordinary, it represents one of the most profound moments in physics. Once inside the event horizon, every possible future path leads deeper toward the center. The journey inward becomes inevitable. Signals can no longer reach the outside universe. Messages cannot escape. The travelers become permanently separated from everything beyond the horizon. This silent boundary therefore represents a point of no return, not because of a physical barrier, but because of the extraordinary way gravity reshapes the structure of space and time. And beyond this boundary, the environment becomes even stranger. As gravity continues to grow stronger, and the true inner mysteries of the black hole slowly begin to reveal themselves. As we continue our quiet exploration deeper into the strange environment surrounding black holes, we begin to notice something remarkable about light itself. In everyday life, light feels constant and reliable. It travels in straight lines, it reflects from surfaces, and it allows us to see the world clearly around us. Yet near a black hole, even light must follow the bending shape of space, and this creates some of the most beautiful and unusual phenomena anywhere in the universe. To understand this, we first need to imagine space not as an empty void, but as a kind of invisible structure that can bend and curve when massive objects are present. Large masses like stars and planets slightly curve the surrounding space. Normally, this curvature is gentle and difficult to notice, but a black hole contains so much mass compressed into such a tiny region that the bending of space becomes extreme. Light always travels along the natural paths created by the shape of space. In normal regions of the universe, these paths appear straight. But when space curves strongly, those paths also curve. As a result, light passing near a black hole begins to bend dramatically around it. This effect is known as gravitational lensing. It means that the black hole can act like a cosmic lens that bends and distorts the light from distant stars behind it. If you were floating in space near a black hole, you might see the background stars appear stretched into arcs and rings surrounding the darkness. One of the most striking possible views is something called an Einstein ring. When light from a distant star passes exactly behind a black hole relative to an observer, the curved paths of light can form a glowing circular ring around the black hole. The ring appears because the light has been bent all the way around the massive object before reaching the observer. These strange visual effects show us that a black hole does not simply swallow light instantly. Instead, light can orbit around the black hole before escaping if it travels along the right path. There exists a special region around a black hole where photons, the particles of light, can actually move in circular orbits. This region is called the photon sphere. It lies just outside the event horizon. Here, gravity is strong enough to bend light into complete loops around the black hole. A beam of light entering this region at the right angle could circle the black hole many times before finally escaping or falling inward. The existence of the photon sphere creates another fascinating possibility. In theory, light emitted from a single star behind the black hole might circle around the black hole several times before reaching an observer. This could produce multiple distorted images of the same star appearing in different positions around the black hole. These effects make the region near a black hole visually complex and strangely beautiful. Instead of seeing a simple dark circle, an observer would see layers of warped light, glowing rings, and distorted star fields bending around the darkness. Even the black region itself is not exactly the true size of the black hole. Because light paths bend around it, the visible shadow appears larger than the actual event horizon. This shadow is what astronomers detected in the first direct image of a black hole released in 2019, when telescopes working together across the planet captured the glowing rings surrounding the dark center of a distant supermassive black hole. The image revealed a bright ring of heated gas swirling around a dark circular shadow. That shadow marked the region where light could no longer escape. It was the visible sign of a black hole, something that for decades had existed only in theoretical calculations. But the story of light near a black hole does not end with bending and rings. Gravity also affects the energy of light itself. When light climbs away from a strong gravitational field, it loses energy and its wavelength stretches. This process is known as gravitational redshift. Near a black hole, this stretching becomes dramatic. Light, leaving the inner regions of the accretion disk, becomes redder and weaker as it escapes the powerful gravity. To distant observers, the light appears shifted toward longer wavelengths. The closer light originates to the event horizon, the more extreme this effect becomes. Eventually, light emitted extremely close to the horizon may lose so much energy that it fades into invisibility by the time it reaches distant observers. In this way, black holes do not simply hide light. They twist it, bend it, stretch it, and sometimes trap it in looping paths around their immense gravity. The region around a black hole, therefore, becomes a place where the simple behavior of light transforms into something far more complex and mesmerizing, revealing how gravity can shape not only matter, but the very paths along which light travels through the universe. As we continue drifting deeper into the environment surrounding a black hole, something even stranger begins to appear. Not only does space bend under the influence of gravity, but time itself begins to change its rhythm. In our daily lives, time feels steady and predictable. Seconds pass at a constant pace, and the flow of time seems identical everywhere on Earth. Yet, the universe does not treat time as something fixed and universal. Instead, time is closely connected to gravity, and near extremely massive objects, the flow of time can begin to slow. This idea may sound abstract at first, but it is a natural result of how the universe is structured. Space and time together form what scientists call space-time, a single interconnected fabric that defines the stage where all events in the universe unfold. When large amounts of mass exist in one place, they bend this fabric. And when space-time bends, both space and time are affected. Near planets, the effect is extremely small. Time on Earth moves only slightly slower than time far away in deep space. The difference is so tiny that we cannot notice it in everyday life. But modern technology such as satellite navigation systems must account for this effect because extremely precise clocks can measure the difference. Near a black hole, the effect becomes enormous. As an object approaches the intense gravitational field surrounding a black hole, the flow of time for that object begins to slow relative to distant observers. This phenomenon is known as gravitational time dilation. The deeper an object moves into the gravitational field, the slower time passes compared to regions farther away. Imagine two clocks. One clock remains far away in empty space, while the other slowly travels toward a black hole. To the observer far away, the clock near the black hole begins to tick more slowly. Seconds stretch into longer moments, and the flow of time gradually drifts apart between the two locations. If the clock continues approaching the event horizon, the slowing becomes more and more dramatic. From the viewpoint of the distant observer, the clock appears to move almost in slow motion. Each second takes longer to pass. Eventually, the clock seems to nearly stop as it approaches the horizon. This effect also explains why objects falling toward a black hole appear to freeze near the edge when viewed from far away. The light signals carrying information about the falling object take longer and longer to escape the strong gravity. The object appears to slow down and fade gradually from view. But for the traveler falling toward the black hole, the experience would feel very different. Their own clock continues ticking normally. Their heartbeat remains steady. Their thoughts proceed at the same pace they always have. To them, the outside universe would appear to speed up instead. As they fall closer to the event horizon, distant stars might appear to move faster across the sky. Time far away in the universe would seem to pass more rapidly compared to their own clock. This strange difference between observers shows that time in the universe is not absolute. It depends on where you are and how strong the surrounding gravity is. The idea becomes even more fascinating if we imagine hovering extremely close to a black hole without crossing the event horizon. If a spacecraft could somehow remain just outside the horizon, and then later return to a distant region of space, the travelers might discover that much more time had passed in the outside universe. Years or even centuries might have unfolded elsewhere, while only a short time passed for them near the black hole. In this sense, black holes behave like natural time machines, not because they allow travel into the past, but because they allow time to pass at dramatically different rates in different regions of space. These effects have been explored in many scientific discussions, and even in science fiction stories, because they reveal how deeply gravity influences the structure of reality. The closer we move toward the center of a black hole, the more extreme these distortions of time become. Near the event horizon, the slowing of time becomes so intense that from the outside perspective, it appears to nearly stop completely. Yet inside the black hole, time continues moving forward in a very unusual way, guiding everything inward toward the mysterious core where gravity becomes stronger than anything else in the known universe. And as the journey continues deeper beyond the horizon, another strange transformation begins to appear, because the powerful gravity of a black hole does not only slow time, it can also stretch objects themselves into shapes that seem almost impossible. As we drift deeper into the strange environment surrounding a black hole, the effects of gravity continue to grow stronger and stranger. Gravity is something we are familiar with in everyday life. It keeps our feet on the ground and pulls objects gently downward when we drop them. Yet near a black hole, gravity behaves in a far more extreme way. Instead of pulling evenly on an object, it begins to pull with different strengths across different parts of the same object. This difference in gravitational pull creates a powerful stretching effect that scientists often describe with a curious name, spaghettification. The name may sound humorous, but the process itself reveals how intense gravity can become near a black hole. The idea is based on something called tidal forces. Tidal forces occur whenever gravity pulls more strongly on one part of an object than another. Even on Earth, tidal forces exist. The moon pulls slightly more strongly on the side of Earth closest to it than on the far side, and this difference helps create the ocean tides that slowly rise and fall across our planet. Near a black hole, these tidal forces become extraordinarily powerful. Imagine an astronaut drifting feet first toward a black hole. The astronaut's feet would be slightly closer to the black hole than the astronaut's head. Because gravity grows stronger with decreasing distance, the feet would feel a stronger pull than the head. The difference may begin small, but as the astronaut approaches the black hole, the difference grows larger and larger. Gradually, the astronaut would feel their body being stretched along the direction toward the black hole. At the same time, gravity would compress the body from the sides. This combination of stretching and squeezing causes objects to become long and thin, somewhat like strands of spaghetti, which is why the process earned its unusual name. For smaller black holes, This stretching could begin even before reaching the event horizon. The tidal forces near these black holes become extremely strong very quickly. Objects approaching them may be torn apart long before crossing the invisible boundary. However, for extremely massive black holes, the situation becomes slightly different. The event horizon of a supermassive black hole can be enormous, sometimes larger than the orbit of planets. In such cases, the tidal forces at the horizon itself may actually be relatively gentle. An astronaut falling into one of these giant black holes might cross the event horizon without immediately feeling the stretching effect. But deeper inside, the gravitational difference would eventually grow stronger and stronger until the stretching becomes unavoidable. The same forces that stretch objects also act on stars and clouds of gas that wander too close to a black hole. When a star drifts near the intense gravitational field, it can be torn apart by tidal forces. The outer layers of the star begin to stretch into long streams of glowing gas. Astronomers have observed events where entire stars appear to be pulled apart by black holes in distant galaxies. These events are sometimes called tidal disruption events. As the star is stretched and shredded, the gas spirals around the black hole, forming a bright, swirling disk that can shine across enormous distances. These dramatic cosmic events help scientists detect otherwise invisible black holes. The sudden flare of light from a disrupted star reveals the presence of a powerful gravitational source hiding in the darkness. Spaghettification, therefore, is not only a strange theoretical idea. It is part of the real physics that shapes the environment near black holes. Yet even this stretching effect is only one part of the experience of falling toward a black hole. As gravity continues to grow stronger, the traveler would notice other strange changes around them. The outside universe might appear increasingly distorted. Light from distant stars could bend into unusual shapes around the black hole, and time itself would continue behaving differently depending on where the observer is located. Eventually, the falling traveler would cross the event horizon and move into a region where the familiar structure of space begins to transform completely. Directions that once pointed outward now led only inward. Every possible future path through space-time begins guiding matter toward the mysterious center hidden deep within the black hole. It is a place where gravity reaches unimaginable intensity, and where some of the most profound questions about the universe begin to emerge. As we continue this quiet exploration of black holes, we can imagine a thought experiment that scientists often discuss. What would it actually feel like to fall into a black hole? From a distance, black holes appear as distant cosmic objects, dark regions surrounded by glowing disks of gas and distorted light. But imagining the journey inward helps reveal how strange and fascinating the physics around them truly is. Picture a spacecraft slowly approaching a black hole somewhere in deep space. At first, the experience might feel almost normal. The spacecraft engines gently guide the vessel forward, while distant stars fill the darkness ahead. Gravity grows stronger as the craft moves closer. But if the approach is slow and controlled, the astronauts inside might not feel dramatic changes immediately. As the spacecraft approaches the region around the black hole, something unusual begins to appear in the sky. The stars behind the black hole would start to distort and bend. Because gravity curves space, the paths of light from distant stars would arc around the black hole before reaching the spacecraft. Instead of seeing stars in their normal positions, the crew would see warped patterns of light forming glowing arcs around a dark center. The closer the spacecraft travels, the more dramatic these distortions become. The black hole itself would appear as a dark circular shadow surrounded by a bright glowing ring of gas from the accretion disk. The disk might shine intensely, swirling at enormous speeds while emitting powerful radiation. If the spacecraft continued drifting inward, the crew would eventually approach the event horizon, the invisible boundary marking the point of no return. From far away, the horizon cannot be seen directly, but its effects begin to shape everything around it. From the viewpoint of the astronauts inside the spacecraft, the crossing of the event horizon might feel surprisingly calm. There would be no physical surface to strike and no visible wall to pass through. Space simply continues inward. Yet something profound has happened at that moment. Once the spacecraft crosses the event horizon, every possible path forward leads deeper into the black hole. Escaping becomes impossible not because of a barrier, but because space itself curves inward so strongly that outward directions no longer exist. Looking back toward the outside universe, the astronauts might see the distant stars compressed into a strange glowing patch behind them. Light from the entire universe would appear to focus into a smaller region of the sky as the curvature of space redirects incoming light. Time outside the black hole might also appear to behave strangely. Because of the extreme gravitational effects, the outside universe could seem to accelerate from the perspective of the falling travelers. Events that would normally take years might appear to unfold more quickly. However, the astronauts would not have unlimited time to observe these effects. As they continue falling deeper, the gravitational differences between different parts of the spacecraft begin to increase. The tidal forces that cause spaghettification grow stronger as the distance to the center decreases. Gradually, the front of the spacecraft would feel a stronger pull than the rear. Structures would begin to stretch along the direction toward the center. If the black hole were small, this stretching might begin quickly after crossing the event horizon. If the black hole were extremely massive, the crew might travel some distance inward before noticing these forces growing stronger. The environment inside the black hole would also grow darker and more isolated. No signals could escape to the outside universe. Radio transmissions would never reach distant observers. The spacecraft and its crew would become permanently hidden behind the event horizon. From that moment onward, their journey becomes one of the most mysterious paths in the entire cosmos. Everything moves steadily toward the center of the black hole, toward a region where gravity becomes so intense that the normal laws describing matter and space begin to reach their limits. Deep inside lies the most mysterious point of all, a place called the singularity. It is a region where matter may be compressed beyond any known structure and where the curvature of space becomes extreme beyond current understanding. For the falling travelers, the journey inward would continue inevitably toward that hidden center. And although the outside universe might never know what happened beyond the event horizon, the silent interior of the black hole would hold the final moments of the voyage within its immense gravity. As we continue our slow and quiet journey through this strange environment surrounding black holes, we begin to notice something that may seem surprising at first. Even though black holes themselves are completely dark, the regions around them can be among the brightest places in the entire universe. This brightness comes from a structure that often forms around black holes, a swirling ring of glowing matter known as an accretion disk. To understand how an accretion disk forms, we can imagine what happens when gas, dust, or even entire stars drift too close to a black hole. Gravity begins pulling the material inward, but instead of falling straight toward the center, the matter usually begins to rotate around the black hole. This happens because most objects in space already have some sideways motion when they approach a massive body. As the material falls inward, it begins to spiral around the black hole in a flattened disk shape. Each particle moves along curved paths, while slowly losing energy and drifting closer to the center. Over time, this rotating structure becomes extremely dense and extremely hot. Inside the accretion disk, particles collide with each other constantly. Gas clouds rub against neighboring streams of matter, and these collisions create friction. The friction generates enormous heat. Temperatures inside the inner regions of the disk can rise to millions of degrees. At these temperatures, the gas begins to glow intensely. The disk radiates powerful energy across many wavelengths, including visible light, ultraviolet radiation, and even X-rays. For distant observers, this glowing disk can appear as a brilliant ring surrounding the dark shadow of the black hole. In fact, some of the brightest objects ever observed in the universe are powered by matter falling into supermassive black holes. When enormous quantities of gas feed the accretion disk, the energy released can outshine entire galaxies. These objects are known as quasars, and they can be seen across billions of light years of space. Quasars reveal how powerful black holes can become when they are actively consuming surrounding material. The energy produced by the accretion disk does not come directly from the black hole itself. Instead, it comes from the gravitational energy released as matter falls deeper into the powerful gravitational field. As the material spirals inward, it accelerates to incredible speeds. In the inner regions of the disk, the gas may orbit the black hole at a significant fraction of the speed of light. The combination of extreme speed and intense compression releases vast amounts of energy. Another remarkable feature, sometimes associated with accretion disks, is the formation of enormous jets of energy shooting outward from the region near the black hole. These jets are narrow beams of high-energy particles that travel thousands or even millions of light years into space. The exact mechanism behind these jets is still being studied, but scientists believe strong magnetic fields interacting with the rotating disk play a major role. As the disk spins, the magnetic fields twist and channel energy along the rotation axis of the system, launching streams of particles outward at nearly the speed of light. These jets can influence the surrounding galaxy by heating interstellar gas and shaping the formation of stars. In this way, black holes are not just destructive objects. They can also help regulate the evolution of galaxies over cosmic time. The accretion disk, therefore, represents a fascinating contrast to the darkness of the black hole itself. While the event horizon hides everything inside from the outside universe, the surrounding disk becomes a brilliant beacon, revealing the presence of the invisible giant at its center. Even the famous first image of a black hole captured by astronomers revealed this structure clearly. Instead of seeing the black hole directly, the image showed a glowing ring of hot gas surrounding a dark circular shadow. That shadow marked the region where light could no longer escape. Through the study of accretion disks, scientists continue learning about how black holes grow and interact with their environments. Each swirling disk of matter tells a story of gravity, energy, and motion, playing out across some of the most extreme conditions found anywhere in the universe. And as we continue moving deeper into the story of black holes, another question begins to appear quietly in the background. If black holes can release such enormous energy through their surroundings, how do these mysterious objects influence the much larger structures of the universe, including the galaxies that contain them? As we continue drifting calmly through the mysteries of black holes, we begin to notice that these objects are not always quiet cosmic traps. While the inside of a black hole remains hidden and silent, the region surrounding it can become one of the most energetic environments anywhere in the universe. Gas swirling through accretion disks, intense magnetic fields, and enormous gravitational forces combine to create powerful storms of energy that can stretch across vast distances in space. The moment matter begins falling toward a black hole, it starts converting gravitational energy into heat and radiation. Every particle moving inward accelerates as gravity pulls it deeper into the gravitational well. This acceleration releases energy in a similar way to an object gaining speed while falling toward the ground. Except near a black hole, the energy involved becomes unimaginably large. Within the inner regions of the accretion disk, the gas becomes so hot that atoms lose their electrons and form plasma, a highly energetic state of matter made of charged particles. This plasma moves rapidly around the black hole while powerful magnetic fields twist and bend through the swirling material. Magnetic fields play an important role in shaping the behavior of the gas. As the plasma rotates around the black hole, the magnetic fields become tangled and stretched. The motion of the charged particles interacts with these magnetic fields, creating complex patterns of energy transfer throughout the disk. Sometimes the energy stored within these magnetic fields becomes so intense that it suddenly releases in powerful bursts. These bursts can produce enormous flares of radiation that briefly make the region around the black hole even brighter. Astronomers observing distant galaxies often detect these sudden flashes, revealing that something extremely energetic is happening near the hidden center. In certain situations, The rotating disk and magnetic fields create one of the most spectacular structures associated with black holes: powerful relativistic jets. These jets are narrow beams of high-energy particles that shoot outward from the region above and below the black hole. The particles within these jets can travel at speeds extremely close to the speed of light. As they move through space, they emit radiation across many wavelengths, including radio waves, visible light, and X-rays. Some of these jets extend for thousands or even millions of light years, stretching far beyond the galaxy that hosts the black hole. From a distance, these jets appear like enormous cosmic lighthouses, projecting energy into the surrounding universe. They can influence vast regions of space by heating clouds of gas and preventing them from collapsing into new stars. In this way, black holes can actually help regulate how galaxies evolve over time. Another dramatic phenomenon that can occur near black holes involves the destruction of entire stars. Occasionally, a wandering star drifts too close to the intense gravitational field. When this happens, the difference in gravitational pull between the near side and the far side of the star becomes enormous. The star begins to stretch and distort under these tidal forces. Eventually, the structure of the star can no longer hold together and the star is torn apart. Streams of glowing gas spread outward before being pulled into the accretion disk around the black hole. As this gas spirals inward, it releases enormous amounts of energy, producing a brilliant flare that can be detected across distant galaxies. Astronomers call these events tidal disruption events, and they provide important clues about the hidden black holes at the centers of galaxies. Even though black holes themselves emit no light, the energy produced by the matter around them can illuminate their presence across the universe. Through these energetic processes, scientists have discovered black holes in places that would otherwise remain completely invisible. In many ways, black holes act like cosmic engines. Their immense gravity converts matter into energy with remarkable efficiency. The storms of radiation, jets of particles, and glowing disks surrounding them reveal that these objects are far from simple dark voids. Instead, they are dynamic centers of activity, where gravity, energy, and motion interact in some of the most extreme conditions known in the universe. And as our journey through the mysteries of black holes continues, we begin to see that their influence does not stop at the small region around them. Many of the largest structures in the universe, entire galaxies filled with billions of stars, may be quietly shaped by the powerful gravitational presence of black holes hidden deep within their centers. As we slowly continue this quiet journey through the mysteries of black holes, we begin to notice something remarkable about their role in the universe. Black holes are often imagined as isolated objects drifting silently through space, but in reality, many of them are deeply connected to the largest structures in existence. Entire galaxies containing billions of stars. Hidden at the centers of these vast cosmic cities, black holes quietly influence the motion of stars, the flow of gas, and even the long-term evolution of galaxies themselves. When astronomers began studying the centers of galaxies more closely, they discovered something surprising. Many galaxies contain extremely massive black holes at their cores. These objects are not small remnants of collapsed stars. Instead, they are enormous gravitational giants known as supermassive black holes. Their masses can range from millions to billions of times the mass of our Sun. These supermassive black holes sit deep within the central regions of galaxies, where enormous numbers of stars orbit around them. The stars move in complex patterns shaped by the powerful gravitational influence of the black hole and the surrounding mass of the galaxy. Even though the black hole itself occupies a tiny region compared to the entire galaxy, its presence plays an important role in the structure of the galactic center. Astronomers discovered these hidden giants by carefully observing the motion of stars near the centers of galaxies. When stars orbit an invisible object at extremely high speeds, it reveals the presence of a massive gravitational source that cannot be seen directly. By measuring these motions, scientists can estimate the mass of the hidden object at the center. In many cases, the results point to objects far too massive and compact to be anything other than black holes. Over time, evidence continued to grow that supermassive black holes are extremely common. Today, scientists believe that most large galaxies in the universe contain one at their center. Even our own galaxy, the Milky Way, hides a supermassive black hole deep within its core. This object lies about 26,000 light-years away from Earth in a region of space filled with dense clouds of gas and dust. Although the black hole itself cannot be seen directly, astronomers have tracked the motion of nearby stars orbiting around an invisible center. These stars move at incredible speeds along curved paths, revealing the gravitational presence of a black hole with a mass of roughly 4 million suns. This hidden object is known as Sagittarius, a star. Even though it is massive beyond ordinary imagination, the black hole at the center of the Milky Way is relatively quiet compared to those in some other galaxies. It currently consumes only small amounts of gas and dust drifting through the region. Because of this, the surrounding accretion disk is faint and does not produce enormous jets or powerful radiation storms like those seen in active galaxies. In other galaxies, however, the central black hole can become extremely active. When large amounts of gas fall into the accretion disk, the energy released can create bright galactic centers known as active galactic nuclei. These regions can shine so intensely that they outshine the combined light of billions of stars in the host galaxy. The jets produced by these active black holes can extend far beyond the galaxy itself. As the jets move outward, they interact with clouds of gas surrounding the galaxy, heating them and sometimes preventing them from collapsing into new stars. This process creates an interesting balance within galaxies. While black holes may seem destructive, they also help regulate the growth of galaxies. By heating and pushing away gas, they can slow down star formation and prevent galaxies from growing too rapidly. Scientists believe this feedback between black holes and galaxies may explain why the masses of supermassive black holes are closely related to the sizes of the galaxies that host them. Somehow, over billions of years, galaxies and their central black holes appear to grow together, influencing each other through complex gravitational and energetic interactions. This connection reveals that black holes are not just strange cosmic curiosities hidden in the darkness. They are deeply woven into the structure of the universe itself. From the quiet center of a galaxy, a black hole can shape the motion of stars, influence the birth of new stellar systems, and release enormous energy into the surrounding space. The invisible gravity of these objects quietly participates in the long story of cosmic evolution, unfolding across billions of years. And as we continue exploring their mysteries, another question naturally begins to emerge. If black holes can grow to such enormous sizes and influence entire galaxies, how large can these cosmic giants truly become? And what are the largest black holes that exist in the universe today? As we continue drifting deeper into the quiet mysteries of black holes, we arrive at one of the most astonishing discoveries modern astronomy has revealed. While some black holes are formed from the collapse of massive stars and may contain only a few times the mass of our sun, there exists another class of black holes that are vastly larger. These are the supermassive black holes, the enormous gravitational giants that sit at the centers of galaxies across the universe. Supermassive black holes are difficult to fully comprehend because their scale stretches far beyond anything we encounter in everyday experience. Instead of being only a few kilometers wide, like a stellar black hole, the event horizon of a supermassive black hole can extend across distances comparable to the orbit of planets, or even larger. Some of them contain millions, hundreds of millions, or even billions of times the mass of our sun. Despite their incredible size, they remain almost perfectly hidden in darkness. Like all black holes, they emit no light of their own. The only way we detect them is by observing how they influence the motion of nearby stars and gas, or by studying the brilliant energy released when matter falls toward them. The existence of supermassive black holes puzzled scientists for many years. When black holes were first predicted through the mathematics of gravity, it was expected that they would form primarily from the collapse of large stars. But a collapsing star can only create a black hole with a limited mass. This raised a fascinating question. How did the universe produce black holes that are millions or billions of times larger than the Sun? Astronomers are still studying this mystery, but several possible explanations have emerged. One idea suggests that the earliest generations of stars in the young universe were far larger than most stars we see today. When these giant stars ended their lives, they may have collapsed into relatively massive black holes that later continued growing over billions of years. Another possibility is that enormous clouds of gas in the early universe collapsed directly into black holes without forming stars first. In regions where gravity pulled vast amounts of matter together extremely quickly, the gas may have compressed directly into a massive black hole seed. Once a black hole forms, it can continue growing by capturing surrounding material. Gas drifting through the center of a galaxy can spiral inward through an accretion disk and eventually cross the event horizon. Stars that wander too close may also be disrupted and partially consumed. In some cases, even entire black holes may merge together when galaxies collide. Over billions of years, these processes allow black holes to slowly increase their mass. The result is the formation of supermassive black holes that dominate the centers of galaxies. One of the most fascinating aspects of these giant black holes is the scale of their gravitational influence. Although the event horizon itself may be enormous, it still occupies only a tiny fraction of the entire galaxy. Yet the black hole can affect the motion of stars across a significant region around the galactic core. Stars orbit the center in complex paths shaped by both the mass of the galaxy and the central black hole. Near the core, some stars move at incredible speeds, completing an orbit in only a few years despite traveling across vast distances. Astronomers have carefully tracked the orbits of such stars near the center of our own galaxy. These measurements provided some of the strongest evidence that a supermassive black hole resides there. By studying how quickly the stars move, scientists were able to calculate the mass of the invisible object guiding their motion. The result revealed a black hole with a mass roughly 4 million times that of the Sun, quietly resting at the center of the Milky Way. In other galaxies, scientists have discovered even larger examples. Some supermassive black holes contain billions of solar masses and power extremely bright galactic centers, known as quasars. These quasars shine across enormous cosmic distances, allowing astronomers to study the universe as it existed billions of years ago. Despite their immense size, supermassive black holes remain deeply mysterious. Their formation, growth, and influence on galaxies continue to be active areas of research. Each new observation reveals more about how these gravitational giants participate in shaping the universe. Yet even these enormous objects are only part of the larger story. Beyond the structure of galaxies and the growth of supermassive black holes, another fascinating phenomenon sometimes occurs when two black holes approach one another in space. When this happens, gravity itself can ripple through the universe in waves that travel across the cosmos, carrying with them the signature of one of the most powerful events known in astrophysics. As we continue this calm exploration through the deep mysteries of black holes, we can now turn our attention to something very close to home on a cosmic scale. Hidden deep within the center of our own galaxy, there exists a massive and mysterious object, a supermassive black hole that quietly sits at the heart of the Milky Way. Although it lies tens of thousands of light years away from Earth, it plays an important role in shaping the motion of stars in the central region of our galaxy. The Milky Way is an enormous spiral galaxy containing hundreds of billions of stars, vast clouds of gas and dust, and countless planetary systems slowly orbiting the galactic center. If we could travel far above the galaxy and look down upon it, we would see long spiral arms stretching outward from a dense glowing core. Deep inside that central core lies a region known as the galactic center. It is an extremely crowded and energetic place where stars are packed closely together, and clouds of gas move through complex gravitational currents. Hidden within this region is the supermassive black hole known as Sagittarius, a star. The name may sound unusual, but it comes from the constellation Sagittarius, where the center of the Milky Way appears in the night sky when observed from Earth. The symbol a star simply indicates that it is the brightest radio source in that region of space. Sagittarius, a star, cannot be seen directly with ordinary telescopes because thick clouds of gas and dust block visible light from reaching us. However, astronomers have found ways to observe the region using infrared telescopes and radio instruments that can detect signals passing through the dust. By studying the motion of stars extremely close to the galactic center, scientists made a remarkable discovery. Several stars orbit an invisible point in space with incredible speed. Some of these stars complete their entire orbit in only a few decades, moving through space faster than almost any stars elsewhere in the galaxy. When astronomers carefully mapped these orbits, they realized that the stars were circling around a massive but invisible object. The mass required to hold those stars in such tight orbits could only belong to something extremely compact and incredibly heavy. The calculations revealed an object containing roughly 4 million times the mass of the Sun, compressed into a region smaller than our solar system. The only known object capable of such density is a black hole. This discovery provided some of the clearest evidence that supermassive black holes truly exist at the centers of galaxies. For their work tracking these stellar orbits, 2 astronomers later received the Nobel Prize in Physics. Although Sagittarius, a star, is massive, it is currently in a relatively quiet state compared to some other galactic centers. Only small amounts of gas and dust fall into the black hole from time to time. Because of this, the surrounding accretion disk is faint and does not produce the enormous jets and bright quasars seen in more active galaxies. Yet even in its quiet state, Sagittarius, a star, occasionally produces small flares of energy when pockets of gas spiral inward. These flares can be detected by space telescopes observing the center of the galaxy. In 2022, astronomers achieved another historic milestone. Using a global network of radio telescopes known as the Event Horizon Telescope, they captured the first image of the shadow of Sagittarius, a star. By combining signals from telescopes across Earth, scientists effectively created a planet-sized observatory capable of resolving extremely small details in distant space. The resulting image revealed a glowing ring of hot gas surrounding a dark central region. That dark shadow marked the silhouette of the black hole itself against the glowing material around it. Seeing this image confirmed what decades of observations had suggested. At the heart of our galaxy sits a supermassive black hole, quietly influencing the stars around it. Although it may sound dramatic to imagine such an object in the center of our galaxy, it is actually very far away from our solar system. At a distance of about 26,000 light-years, it poses no danger to Earth or to the planets orbiting our Sun. Instead, it simply continues its silent presence at the galactic center, while billions of stars, including our Sun, slowly orbit around it over vast spans of cosmic time. And yet black holes are not always solitary objects. In the vast dance of galaxies across the universe, there are moments when galaxies collide and merge. When this happens, the massive black holes at their centers may eventually meet each other in deep space. When 2 black holes begin spiraling together, the result becomes one of the most powerful and fascinating events known in the universe. As we continue our calm journey through the universe of black holes, we arrive at one of the most powerful and dramatic events that can occur in the cosmos. Although black holes often exist alone at the centers of galaxies, the universe itself is constantly changing. Galaxies slowly move through space, and over billions of years, many of them eventually collide and merge together. When this happens, something extraordinary may occur deep within their centers. The supermassive black holes of those galaxies can begin a slow gravitational dance that eventually leads to a collision. Galactic collisions are not sudden crashes like two solid objects striking each other. Instead, they are slow cosmic interactions unfolding over millions of years. Stars from the merging galaxies usually pass by each other without direct contact because the distances between them are enormous. Yet gravity reshapes the structure of both galaxies as their stars, gas clouds, and dark matter begin to mix together. During this process, the supermassive black holes that once sat quietly in the centers of the original galaxies begin drifting toward one another. Each black hole carries enormous mass and therefore powerful gravity. As they move through the dense central region of the newly merging galaxy, they gradually lose energy through gravitational interactions with surrounding stars and gas. Over long periods of time, the two black holes move closer and closer together until they begin orbiting each other. At this stage, they form what scientists call a binary black hole system. The two massive objects circle around their shared center of gravity in an ever-tightening orbit. As the orbit shrinks, something remarkable begins to happen. The movement of the black holes disturbs the structure of space-time itself. According to our understanding of gravity, large accelerating masses can create ripples in space-time that travel outward across the universe. These ripples are known as gravitational waves. Gravitational waves are incredibly subtle disturbances in the fabric of space-time. As they pass through space, they slightly stretch and compress distances. The effect is extremely small. Even powerful events create waves that change lengths by fractions of the size of an atomic nucleus. Yet despite their tiny size, these waves carry enormous amounts of energy across the universe. As two black holes spiral closer together, the gravitational waves they produce grow stronger and stronger. Energy carried away by the waves causes the orbit to shrink even faster. Eventually, the black holes approach each other at incredible speeds. In the final moments before the collision, the two black holes circle each other many times per second. Their immense gravitational fields twist and distort the surrounding space-time in dramatic ways. Then suddenly, the two horizons merge into a single larger black hole. At that instant, a powerful burst of gravitational waves spreads outward through the universe. These waves travel across billions of light years, carrying information about the masses and motion of the colliding black holes. For a long time, gravitational waves existed only as a prediction of theoretical physics. Scientists believed they should exist, but detecting them seemed almost impossible because the signals reaching Earth would be extremely faint. That changed in 2015 when scientists using an observatory called LIGO made the first direct detection of gravitational waves. The signal they detected came from two black holes that had collided more than 1 billion light years away. Sensitive instruments measured tiny changes in distance caused by the passing waves. The detection confirmed that gravitational waves truly exist and that black hole collisions are real events happening across the universe. Since that historic discovery, many more gravitational wave signals have been detected from merging black holes and neutron stars. Each detection provides new information about the extreme environments where these events occur. Through these observations, scientists have opened an entirely new way of studying the universe. Instead of observing only light from distant objects, we can now detect the subtle vibrations of space-time itself. Black hole collisions, therefore, represent not only some of the most energetic events in existence, but also a new window into understanding gravity and the deep structure of the cosmos. Yet even as we learn about the dramatic interactions between black holes, another mystery continues to wait at the center of every one of them. Hidden beyond the event horizon lies the most extreme region of all, the mysterious point where gravity becomes so intense that our understanding of physics begins to reach its limits. As we gently continue this long journey through the mysteries of black holes, we now move toward one of the most fascinating ideas in modern understanding of the universe. What actually happens inside a black hole after something crosses the event horizon? From the outside, we can observe the effects of gravity, the glowing accretion disks, and the motion of nearby stars. But once anything passes beyond the event horizon, it disappears from the observable universe. The interior becomes hidden from every telescope and every signal. Yet even though we cannot observe the inside directly, scientists can still explore the possibilities using our understanding of gravity and space-time. These ideas reveal that the interior of a black hole may be one of the strangest environments anywhere in the universe. Outside of a black hole, space behaves in familiar ways. Directions make sense. We can move forward or backward, left or right, closer or farther from an object. But inside the event horizon, the structure of space-time changes in a remarkable way. In everyday life, time always moves forward. No matter what we do, the future lies ahead, and the past remains behind us. Inside a black hole, the direction toward the center becomes similar to the direction of time itself. This means that once an object has crossed the event horizon, moving toward the center of the black hole becomes unavoidable in the same way that moving forward in time is unavoidable. Just as we cannot stop time from passing, we cannot stop the inward motion once inside the horizon. Even if a spacecraft fired its engines in the opposite direction, the structure of space-time would still guide it deeper inward. Every possible path leads toward the central region of the black hole. This idea may feel difficult to imagine because it challenges our everyday experience of space. We are used to thinking of movement as something we can control by choosing a direction. But inside a black hole, the geometry of space-time itself removes the possibility of moving outward. In this environment, the distance to the center gradually decreases no matter what an object attempts to do. The inward journey becomes part of the natural flow of space-time. Another strange feature of the interior involves the behavior of light. Outside the black hole, light can travel in many directions. Inside the event horizon, all paths of light also lead inward. Even beams of light moving outward relative to a falling observer still move deeper toward the center because space-time itself curves inward. This reveals how powerful the gravitational distortion becomes inside the horizon. The structure of space no longer allows escape paths to exist. As an object continues falling deeper, the gravitational differences between different points become stronger and stronger. Tidal forces stretch objects along the direction of the fall while compressing them from the sides. Over time, this stretching can become extreme. Eventually, the falling matter approaches the deepest region of the black hole, the mysterious center known as the singularity. The singularity is a concept that appears in the mathematical description of black holes. According to these equations, the density of matter becomes infinitely large at this point, and the curvature of space-time becomes infinitely strong. Distances shrink towards zero while gravity grows without limit. However, the idea of infinite density suggests that our current understanding of physics may be incomplete in this region. The laws that describe gravity and matter under normal conditions may no longer fully apply when conditions become so extreme. Because of this, scientists believe that a deeper theory combining gravity with the principles of quantum physics may eventually be needed to fully understand what happens at the soul. Singularity. For now, the singularity remains one of the most mysterious ideas in all of cosmology. It represents a place where the known structure of space and time reaches its limits, and where the universe may behave in ways we do not yet completely understand. What we do know is that inside the event horizon, every object that falls into the black hole continues moving toward this hidden center. The journey cannot be reversed, and no information can escape to tell the outside universe what truly happens there. And yet even this mysterious interior may not be the end of the story. Some theoretical ideas suggest that the extreme conditions inside black holes could connect to other strange possibilities within the universe. Ideas that hint at tunnels through space-time or hidden regions beyond the familiar structure of our cosmos. As we continue this calm exploration through the hidden interior of black holes, we arrive at one of the deepest mysteries known in cosmology. At the very center of a black hole lies a region that scientists call the singularity. It is a concept that appears when we use the equations of gravity to describe what happens when enormous amounts of matter collapse into an extremely small space. In normal conditions, matter always occupies a certain volume. Even the densest objects we know, such as neutron stars, still have a physical size. Inside those stars, matter is compressed so strongly that atoms themselves break apart and particles are pushed tightly together. Yet even neutron stars have limits. Their structure still follows the known laws of physics. A black hole forms when gravity becomes so powerful that even those limits are overcome. When the core of a massive star collapses beyond the stability of a neutron star, the compression continues without stopping. Matter is pushed closer and closer together by the relentless pull of gravity. According to the equations that describe gravity, this collapse can continue until all the mass is concentrated into an incredibly tiny point. At that point, the density becomes unimaginably large, and the curvature of space-time becomes extreme beyond any ordinary description. This theoretical point of infinite density is what we call the singularity. The word singularity reflects the idea that something unusual happens there. Something where the mathematical description of space and time begins to break down. In the equations used to describe black holes, certain values approach infinity at the singularity. Distances shrink toward zero, while gravitational effects grow without limit. This creates a challenge for our understanding of the universe, because infinities in physical equations usually suggest that our model of reality is incomplete. They often indicate that a deeper theory is needed to describe what truly happens under such extreme conditions. At present, our understanding of gravity comes from the theory of general relativity, which describes how mass and energy bend the fabric of space-time. This theory has been tested many times and works extremely well in many environments across the universe. However, general relativity does not include the principles of quantum physics, which describe how nature behaves at extremely small scales. Near the singularity, both gravity and quantum effects should become important at the same time. Because of this, scientists believe that a future theory combining gravity and quantum physics may eventually provide a clearer picture of what happens inside black holes. Such a theory is often referred to as quantum gravity. Until that deeper understanding is developed, the singularity remains a mysterious prediction of our current equations. It represents a region where the known laws of physics reach their limits. If an object falls toward the center of a black hole, it would eventually approach this region of extreme gravity. Long before reaching the singularity, the tidal forces would become incredibly strong. Matter would be stretched and compressed in dramatic ways as space-time itself curves inward more and more steeply. From the perspective of an outside observer, however, none of this can ever be seen directly. The event horizon hides the entire interior from the rest of the universe. No signal from inside can cross that boundary and return to distant observers. This means that the singularity remains forever hidden from direct observation. Everything we know about it comes from mathematical reasoning and indirect clues about the behavior of black holes. Yet even though the singularity is hidden, it plays a crucial role in shaping the structure of the black hole. It represents the final destination of the inward journey once the event horizon has been crossed. In many ways, the singularity marks the deepest point in the known structure of space-time, a place where gravity reaches its ultimate intensity and where the familiar concepts of distance and time may lose their usual meaning. But as scientists continue exploring the mysteries of black holes, some theories suggest that the singularity might not be the true end of the story. Under certain conditions, the extreme bending of space-time might allow connections to form between distant regions of the universe. Strange possibilities, sometimes described as tunnels through space-time itself.